crossed paths for the first time at the professional session in the late 90s. I was a PhD student. You were in staff at Lehigh, where you were not a professor yet, right? And we probably had a year or two, and things kept going ever since. The one thing that there are many things to like about John, and again, I was surprised. You play drums, and I should have known that earlier. But John is unique among us that he grabs like engineering things and puts them to good practice. Very often we do trial and error. Others of us try to do the engineering things and pray for somebody like John to put them to good use, right? So this thing is unique. So I'm not a deep metallurgist. I can do some things here and there, especially when I can translate. But I'm on the side of trying to generate these engineering fundamentals that I pray to God one day are going to be put to good use by you. Let me see. So this is about predictions of thing. The type of thing you do. Where I want to go with this. My ultimate goal is to have a McDonald's franchise. And I'll tell you what. So, well today is not good until you do QA or QC, right? And you're going to tell me a million reasons why that's right. So this is not my own concept, but this is like Dwayne Miller convinced me of that. You sell 2.36 billion burgers a year, and you never did QA or QC on your burger. Think about that. You would have so many more excuses to say I'm not eating it until it passes, right? So that's where I think welding should go, right? And I agree. So that's the ultimate goal. Intermediate goal is, well, you don't get there if you don't know what you're doing. And I'm trying to bring some of this understanding in the little thing I have. So where are the variables and how they play? So the explanations will be based on the laws of nature, which we seldom do, right? And welding works by the grace of God, and that's why we have a prayer breakfast before each right? And then we have these essential variables that are like something broke, and some old guys say, okay, add this to the list of essential variables, right? All this is empirical, debatable, right? It's a list of facts and even debatable facts. They also don't anticipate the effect. If you move the essential variable, you're a bad boy, but you don't even know what's going to happen in what direction. So let's bring some sort of like a understanding on that. So what we have been doing so far is trying to make predictions for all those things. And my hope is that your progeny, John, can take on some of this. So we can predict, and I put a list of those things, right? And the nature of the predictions we do is that they should be feasible for practitioners. So although we do have fancy numerical simulation software, what I care is, can I give you a formula that you can use, but you can trust, right? That a formula that is general, not an interpolation. A formula that is accurate, right? So it would be like an engineering type of thing. Like tables, graphs, map. I'm a Mackey. I deserve my CO2 footprint, but here it's mostly metallurgists, right? So how we do this type of thing? From when it comes to heat transfer, that's where I'm going to be focusing. We look at this and try to calculate what is the maximum width, the peak temperature, those type of things. And you see the symbols, and you see the Mackey-like kind of schematic that you see is some sort of a thermal map. Now, skip many, many years and many, many PhDs. We did this, right? So, we did it, right? I have two Chinese students. Really, they came from the #1 university in China. Each of these things, you see, they have these weird numbers, 0.159. That is, I think, pi over 4 or something weird. But this is not empirical. None of this is empirical. All this comes from analysis, right? And we predict the width. John, you'll appreciate this. This is melting efficiency, which happens to be what you already said, right? But it comes out of the same result, right? We have formulas like those. These numbers here, you see 1, 2, 3, 4, is thick plate, thin plate. Something that people seldom talk is fast or slow, right? Oh, so much more work. Phil Fiersback was a pioneer in all these things. He wrote this paper and invented this Rosenthal number, which I thought I had invented until I found it on the internet. And so credit goes to Phil and other of your guys. And they said 1, 2, 3, 4, for example. Regime 1 would be thick plate moving fast. Regime 3 would be thin plate moving fast. And those dots you have there is because I had the students go through the Lincoln Welding Procedure Handbook, transcribe the whole thing. It's more than 1,000 procedures in Excel, and then plot them in there so we would see. Funny enough, they are all in the intermediate part. So the formulas fall right in between the formulas we have. I can tell you more. If we're talking about cooling, we have formulas, like for example, underwater wet welding, we can predict that kind of okay. If you're talking about distributed sources, right, like these Gaussian heat sources, we have a top hat, but doesn't matter. Like, this is what I wanted to do in life. I wonder what went wrong, but these guys validated it. So you look at their thesis, you look at their papers, you're gonna see these formulas, these curves that look like fluid mechanics books, right? Like saying, oh, here's my formula in dimensionless, and here are the points. You're not that bad. I could spend a bunch of time telling you exactly what this is. This Rosenthal number that is what I thought I had invented, but it's Phil's. So the dimensionless number is similar to the Mach number, but for welding. I could talk much about that. I have 40 minutes. Well, this is like some sort of indication of you're faster or slow in welding in dimensionless terms. Being fast in aluminum is not the same as being fast in titanium, right? We all know that, but I have a number for that. Phil has a number for that, right? And then we can predict with or things like what we have. You can barely read all these things, right? But we can predict cooling rate, thickness of the heat affected zone, and all those dots, those come from a literature survey. We didn't do it. So, yeah, to some extent credible to be in the journal Heat Transfer, credible to me. I'll tell you one problem I have. I do this. I'm serious, right? This obviously will have limitations, but we more or less know the limits. Nobody gets excited by seeing that, right? So, look, that's pretty good. And by the way, so these things are, so what we, oh, I have more. You better believe me, but you don't. Nobody cares. So, what have we done? So, I had these students coming from free from my native Argentina, which is convenient. Anyway, if I pay them, like they will be millionaires with it. And I said, what I want you to do is to do their own test, right? And funny enough, if I tell you I compare with like 50 years of literature, everybody goes, man. I hope now you get more excited because no, now we did the welding. It's like 3 more points, right? But now everybody's excited. So we targeted a few things, right? We have a lab that is ridiculously good. We can do so much, and I do theory. What an unfairness. Anyway, so we have all the welding machines, lasers, whatever we want. We decided to the simplest cases, right? Let's start with TIG, autogenous, bead on plate. I mean, the type of thing people say, when do you want to weld with that? Well, I don't want to weld with that. I want to test the theories, right? And before I test something crazy, I test something small. So I build my reputation, and you guys follow your advisor and put this engineering to good use. Target variables, the width, the depth, and the thickness of the heat affected zone. So the guys did these 12 welds. They had never seen a welding machine. Now they did, and they ran them, and they cut the cross sections, and they measure the heat affected zone, right? And it's not too many welds, but we did them ourselves, right? And they did this experimental matrix that was randomized. We did data acquisition. Those are target values of current, but we did the data acquisition for the current. For speed, the guys, they built an Arduino to measure the travel speed of the table, right? Because we have an old lathe. So much work. Change the arc length. Then I had French guys changing gases. I'm not talking about that now, but it still works. And And I cut to the chase. I typically get excited telling you all about the formulas, but being John's birthday and sparing you of that, I got it. So this is what we got. So if we measure the thickness of the heat affected zone, right? It could be this way or this other way. So let's look at it in the depth, right? And you have this formula there, right? That's the type of things we do, and I think there's a pointer here, better than me. Oh, here, right? This comes from first principles. This is not interpolated. This is not calibrated. No frigging like a fudge factor. And these numbers here, these are universal. You were in Jupiter, you do the math, you get this number, right? And this recanning, not my invention, is the same as a Rosenthal number, but for thick plate, feels beat me to the punch on that one, right? And I can predict this G prime here is a correction factor. But correction factor doesn't mean fudge factor. It's like a huge chunk of equation that comes also from the first principles and dimensionless. And here we have what we predicted with this formula that does not have a fudge factor, does not have calibration, this formula. I repeat, nobody believes that I have this stupid little formula. Some people would say, wow, this is difficult. This is one cell in Excel. And we're predicting things this well, without fudge factor. But this is it, right? And things like thermal conductivity. We accounted for the variable properties. We had a way of getting an effective value that is a constant value, but it accounts, we integrate over all the things very rigorously, right? And we did it with JMAT Pro, we did it with thermocalc, we did it with the literature search, we compare the values, right? Temperatures here, like A1, right? And melting temperature. We had to debate if we use child or we use it, all those things, right? And funny enough, the guys struggle with using shell with steels. That's a question I want to discuss. Anyway, the predictions are pretty good, I'd say, right? I mean, I cannot measure better than this. If I do the weld again, the points scatter in a different way. All of us, whoever did more than one weld, know that. Here's the formula with this G, whatever. So none of this is empirical. All of that comes from doing the asymptotics and all those type of things. All this is like asymptotics. This is no fudge factor. Thickness of the heat affected zone here. This is, I'll tell you more what is crazy about that. When the French guys came, they repeated the experiments. And they got the same. I'm blown away. Okay, it's my same lab, but different people, different day. Right, this I forgot to tell you, but this is for 130 steel, right? But to me, it's transparent. All I wanted is to say something I can predict, right? This is the bead width, not now the heat affected zone. This is trickier. Why is it trickier? Because now I'm talking about the width, and we are melting metal, right? And you might have heard before, like, if you don't have Marangoni, it's all wrong. Okay, but let me tell you about that, because I did my PhD on Marangoni, right? Had another guy from Ukraine doing the PhD on Marangoni. So that depends on the fluid flow and the Becquerel number and a bunch of things. So in some cases it affects, in some cases not. One guy in the lab did a whole PhD about that, and we did all the dimensionless thing. Want to draw your attention to one thing. We already corrected for this, but it's not in this slide. See how the width is a little, the measured width is bigger than the predicted width. Of course, right? This was a very low sulfur steel. We can account for that, right? And we have like, which I did not include here, right? In this very simple situation, right? And it doesn't change very much. And by the way, I think this small difference only gives me credibility. Because if I always cross in the middle, right? But this is impressive. Now let me show you more credibility. Now there is a little bit more scatter. Now we're talking about weld depth, right? And for the weld depth, we predict something, and we measure something that is bigger, like we're a millimeter off, pretty much, right? Depends on the condition. given that everything else was that good, what's happening here? I'll tell you what I think is happening here. I'm gonna show you here. You see, for once I'm having a presentation that is moving according to time. For once, the arc pressure depresses the surface of the well pool, right? I don't know if that is the one cause, right? But we know that that is a fact. So I think this higher penetration in reality that what we predicted is because of the arc depression, which we also know how to tackle. I didn't want to tackle it at this time because I did not expect this to be a problem, right? But we did this surface profilometry, right? We have this like super fancy thing, and it tells us this is surface of the, we cut the current off before we cut the motion. So we freeze the weld in place. And we have this depression. I still don't know why we always end up with a knob sticking out, but we see this depression. So I know for sure that we have, now I can say the truth. So we have this depression that is there. So for sure, at least part of this error that I'm showing you here comes from the surface depression. So now we're measuring with the profilometer all of the things, and we're doing it as I speak to you here. There is a guy measuring it in the lab. So the bottom line is we can predict some features of welds with good accuracy. I've proven that to you. You're gonna say, yeah, Mickey Mouse, like a autogenous thick weld. Well, I can or I cannot. For that one, I can. And probably I feel hopeful, I feel confident that I can increase the difficulty, right? As I bring understanding, right? And this is without fitting and without calibration. I want to emphasize on that. And chances are that 90% of you still don't believe me, but stay with me and go over the equation. This is the simple formulas. I'm selling you a Mercedes at the price of like a little Honda Civic, right? And I'm not saying it can do everything, but I'm saying it is possible. As a mechanical engineer, I grew up thinking that formulas predict reality. As metallurgists, you think formulas is what you put to impress people, but you never, most metallurgy books don't have a table of values to replace in the formulas. I said most, but I've never seen any with a table of values. Mechie books do. What we're trying to do is to have those formulas with tables of values that you replace, and you're more or less on the money, right? We can account for variable material properties. I'm not showing you this to you now, but it's very rigorous, right? So you say, oh, variable material properties, oh yeah, we went to town with that, and we account. Perfect? Not, right? Good enough? Likely yes. We can correct for Marangoni flows, right? We're not making things up in thin air. We're exploring the effects of arc pressure, right? We're also doing similar experiments with laser, right? Because now we don't have the arc pressure. I know for a fact that these formulas work because for laser cladding, we're already using them in industry. And the guys can predict things to a very high degree before they do the laser cladding procedures, right? But I want to do something simpler than laser cladding to start showing people, look, this is what I predict, this is what I get. You could do this yourself. So anyway, I'm giving room for people for coffees, hopefully some questions. Somebody who don't like it, bring it on.
We have plenty of time for questions.
Thank you very much for this great work. I'm a big believer in analytical closed-form solution models too.
Oh, you're my day.
What I've experienced is when my students and I submit papers to journals that use mostly easy-to-use analytical models, the reviewers claim that this is not state-of-the-art. Where's the CFD model with phase field and all this other crap? I think I know what your answer is, but what do you think about that attitude towards these kind of models in the academic literature?
Well, funny enough, I seldom have that response, but when I show the equations, right? Because the way we develop them is different than finite element, or many people say you're submitting the same paper again. Because it's that weird thing that they hadn't seen, and think it's the same weird thing as before, right? So, I think I chose to do what is right. I'm paying a price for that, but still things get published. And at the end of the day, you match or you don't match, right? With the nuances that if you show me a 99% match, I don't believe it, because twice the same well doesn't give you 99%.
And not only does it match or not match, do people use it or not use it? Like Rosenthal, right? Everyone uses Rosenthal's model. I don't know anyone who uses a singular like CFD model over and over across industry, across time, across applications, right? So,
well, Rosenthal is interesting. Many of those formulas, Rosenthal, you say X, Y, Z, and they give you T, temperature, right? But in reality, you know temperature is melting temperature, A1, A3, whatever you want. You don't know where it is. So you have to work it backwards. Right. These formulas we have here, it's working it backwards because the function is not inversible. You have to invert it some way. And again, I thought I had invented a technique, which I didn't, something called blending, in which you do asymptotics and then you do an approximation of the inversion that is typically within 10% accuracy. And I'm okay with that. That's what I'm showing you here. So, sorry, I lost track. What did you say?
well, the last comment I made was, you know, if it matches, then and it's easy to use, people will use it. It actually makes a big impact on the community.
Rosenthal.
Yeah.
So Rosenthal, there are two types of people about Rosenthal. Those who look at the formula and say this is too complex because it's an exponential, and those who look at the formula and say this is too simple because that's right. But there are very few people who actually use Rosenthal, and we're all in a closet. Because when you come out, you're going to be shown as too difficult or too simplistic. I'm a believer, especially for things like T85. Rosenthal doesn't matter for T85. For thickness of the heat affected zone, it's pretty good. And if you say, well, it's not a point, that many times the no point effect matters. We have this paper of Tom Eager with the Gaussian, right? We did the inversion of that, and that's what we were using in this case. And it's a formula, right? And so let's talk some more. Yeah, sorry.
So in the equation Q, does it include the absorption efficiency, or you don't need to?
Hold on. All right, so, I told you, we don't fool around. Efficiency is like a horrible concept. It's tabulated in many books, and you have like a, I don't know, 0.6 to 0.8 or 0.85 for meg, things like those. People believe efficiency is a thing, but in reality, efficiency is how much heat went into the plate, right? And people do something like current times voltage, and then they say how much a percentage of that went in. You have, and this is from measurements we have done about the plasma, right? You have an anode full voltage, a cathode full voltage. Energy distributes between those two. You have the arc column that loses some energy, right? About some fraction of that energy goes to the plate. It's more or less 1/3. We can argue if it's overhead or something. Let's call it 1/3 for now, right? So that's efficiencies. We calculate efficiencies. I don't use efficiencies from a table. I know my anode full voltage because I have measured it in the lab. I know my cathode full voltage. I know the total voltage. So in this case, there's one thing about this that is true, is honest, but we're working on removing. I use measured voltage, right? My real goal is not measuring. If I give you an arc length, you should know the voltage, which we are not too far off, but the scatter was bigger. And we had like another guys measuring the voltage and all that. So here we are calculating the efficiency based on the voltage and the anode full voltage and cathode full voltage, we know. So, Suresh, yeah, that's the answer.
So there is a need to be a measurement done, correct?
In this case, I need to measure the voltage. You're right.
So when you're doing a deployment in the industry level, would you envision putting a sensor to measure this? Or does it change, does not change?
Okay, so you realize that this in particular industry is not asking me about a touching a stick or bead on plate, right? So my ultimate goal is I don't measure the voltage. If I give you an arc length, and by the way, I have formulas for that, but the error in my predictions of voltage with arc length, I still don't get it perfect. I get it quite right, very quite right. So in this case, because I wanted to impress you, and you'd be okay with me measuring voltage, but we can do it without measuring voltage too. The scatter is bigger. So yeah. So ultimately, is what you know before the weld. My goal is to predict the weld before I do the weld. If my prediction is after I did the weld, it comes to question, why did I need the prediction if you asked me for the weld first? Right? There is argument about that, but I want an engineering tool that tells you something reasonable before you do it. Right? So,
Thank you.
I don't really have a question for Patricia, I just wanted to make a couple quick comments. First one, this is really good stuff, really cool stuff. Second one is, I see Phil Firstbach all the time and he cares.
yes, I know.
And the last one is, out of those 2.36 billion burgers, I feel like I'm getting more than my fair share of ones that are, that should have been QC.
Well, you were here to complain, so that bad wasn't it. Yeah. But there is something to be said that in the welding community, we take for granted some things that in other industries are completely taken for granted the other way around. And I think this, if I ask you a very simple problem, you don't need to be very smart to figure it out. If I ask you more and more difficult problem, you need to be more and more smart. But if I ask you a really, really difficult problem, like how we run a country, the level of skill, intelligence doesn't need to go up, right? So this is maximum. I believe welding was right there, a little bit to the right or to the left. So we have taken welding so far a little bit closer to running a country, in which we do it like with a bit of intuition, lots of knowledge. But when you talk to a welding engineer, right, like they kind of try things until they work. And what I'm trying to do is thinking, all right, I think welding is, if we really do all the metallurgy and all the asymptotics and all the right things, I would move it into that. If you're a super guy, then you can predict it. It's kind of there. I think it's possible. But
Great.
All right. Well, on that note, let's thank Patricio again.